Okay, everyone, welcome to our webcast. Today we're going to talk about the Informix SQL Optimizer and how to read this is a fun topic. It sort of goes along with the one I did last month on indexes and the one I did next month on update stats. These three go together. I am Lester Knutsen. Been working with Informix since 1983, back when Informix started as relational database systems, and focused pretty much on Informix only over the last years since that time. Now, a couple of ground rules. The webcast is being recorded, and the replay and the slides will be available in a few days, probably early next week. The second rule is if you could please make sure you stay on mute. Background noise will really distract everybody, and much better if we don't have it. If you have questions, there is a chat button on the screen. Now that WebEx just did a upgrade last night and they've changed where things are. But find the chat button, put your question into the chat. I may not see it right away. When I'm full screen like this, I don't see the chat. If I go to part screen like this, I do see the chat. So that's how you know whether I'll see the chat or not. Right now I can see the chat. Going back to full screen and I won't see the chat. I'm going to dive right into understanding the Informix SQL Optimizer using Sqexplain. This is really how to read the output from the optimizer. Now, to back up a little bit, for every SQL statement that you type, you generate in a program, whatever, when Informix gets that statement, it first checks the syntax, it checks the permissions to make sure that you have permission to the tables you're trying to access. Then it sends the SQL to the optimizer. And the optimizer's task is to decide on the best plan to access the data you have asked for. Then it develops that plan and implements that plan, and you get back data. Now, what the step we're concerned about is this step right here, where the server sends the SQL to the optimizer, and the optimizer decides how to access that data. The goal of the optimizer is to determine the fastest way to get that data. And looks at every possible way of implementing your query. Let's say you have two tables. Each table has 4 indexes. So that means you could access that table by doing a sequential scan or use one of those 4 indexes. So for each table, there are 5 ways of accessing that data. Now with 2 tables, that's 5 times 5. There are 25 ways of accessing that data. And what the optimizer does is it looks at all 25 ways and gives each one a cost, assigns a cost to each access method, and then picks the one with the least cost. Now, it's not a rule-based optimizer. Back in the old days, when I started using Informix, it was rule-based. And the order of tables from left to right would affect how things were read. And the order of things in your where clause will affect how things are read. In one sense, the SQL query optimizers, and all the databases do this, were among the first to put in artificial intelligence to try and figure out the best way to run that query. And it's because data can change. You can start out with an empty database, and the fastest way to do a query might be one way. But as data grows and your tables grow, that may change and a different method may be faster. So it's a dynamic optimizer. And you can run a SQL statement one day and it will run it one way. And then next month, because the data has changed, it may pick a different access method. The optimizer picks an access method on what it thinks will be the fastest way to run your SQL. And what it has to do is determine which table to read first, which index to use first, and if you have filters on the where clause, which filters to use first, and then second, and then third, and fourth. It's all about deciding what order is it going to do in. Now, there are a number of things that affect the optimizer, and the biggest thing is update statistics. Update statistics, which is my webcast next month, tells the optimizer how many rows are in each table and how many pages are in each table and in each index, and then how unique the columns are in an index. It also tells the optimizer what indexes are out there and how many levels there are in an index. If in my webcast last month, I talked about levels in an index and how an index may have 2, 3, or 4 levels. An index with 2 levels is going to be better than an index with 5 levels. The same, if a column is unique, it's going to be better than a column that's not unique. And then the last factor that affects the optimizer is the distribution of data. And this is when you update stats with medium or high, you collect data distributions. And that plays a big role in what the optimizer does. So it takes all this information, turns it around, and says, okay, best way to access data. Now, to see the query plan, you have to turn on explain. And it's a very simple set explain on. We'll turn on explain. And then from that point onward, all your queries will show a file called Sqexplain.out what the query plan is. And then when you're ready to turn it off, you just say set explain off. Or if you disconnect from the server, it will automatically turn off. You can also do set explain on file to, and then give it a file name. And this is what I'm going to use in these examples. This is the preferred way to do it. In fact, if I'm writing a program, I will oftentimes put an if debug flag, then turn this on so that I can run my program. And if something's not working right, I can pass a debug flag to the program and it will then turn on set explain and put the output to the file. The file is very important because if you don't do that, it all goes into a file called Sqexplain.out. This way you can get the query plan by program or by file. Option that I really like is the set explain on avoid execute. Let's say you have an SQL that takes 4 hours to run, and you don't want to run it and spend 4 hours waiting to see the results. Results contain 2 parts. They contain a query plan and the cost, and then the second part is the statistics on how long each part took. If you say set explain on avoid execute, it will show you the first part right away and not run the query. So your query will say no rows returned, but if you had returned rows, here is the query plan the optimizer would have used. And that's very helpful to debug very large programs. I use that when I've got 4 or 5 hour jobs that I want to debug, and I'll go in, run it with avoid execute, look at the cost, maybe make a change, run it again, see if the cost is better, make a change, run it again, see if the cost is better. The fourth option you have to see the query plan is the on mode minus capital Y session ID. And this allows you to dump the query plan of a running query. Now you have to be Informix or a DBA to do this. And there are a couple of ways of running it. If you just do on mode minus capital Y session ID, you don't always know where the output file goes. Sometimes and it depends on the version of Informix you're using, where it goes. Sometimes it'll go in the home directory of the user. Sometimes it'll go in /temp. You really don't know where it's going to go. What I like to do is the on mode minus Y, give it a session ID 1, and then the name of the file. 1 says turn it on, and this gives me a file where I know where it's going to go. And so I can see the SQL explain output for that user's session. Now that will only turn it on for that one session ID. As soon as that session ID is gone, it's turned off and go up again. So what does the SQL explain file show you? First is it shows you the SQL statement that you're optimizing. And this is the most important thing. It gives you a cost in units. And the units is just a number. I've had several discussions with developers about what this means. And the best answer is it's just a number based on I/O and CPU cost, even though it's mostly based on I/O. And it tries to calculate I/O this query is going to take. And so going back to my earlier example, 2 tables, 4 indexes each, 25 access methods, each one of those will have a cost, and it picks the query plan with the lowest cost, and that's what it goes out and does. The next thing it does is it tells you the estimated number of rows that the query is going to produce. This is very important because it tells you if update stats are correct. It says, I estimate 0 rows, and you know there are 1 million rows in the table. Got a problem. And I use this a lot, and I'll show you some examples coming up and how we use this. Then it tells you the order of tables it's going to access. Doing a parallel query, it's going to do one table at a time, and it tells you the access plan it's going to use to access that data. Now, the access plan could be one of 4 things. A sequential scan is very simple. It reads all rows in the sequence that they are in the table. It does not sort them. It's whatever page comes first. In fact, it's guaranteed not to be in order. If you don't have a where clause, that's the fastest way to read data. It's just to do a sequential scan. If Informix thinks a table is empty, this way to read an empty table is to do a sequential scan. Why bother reading indexes if it's an empty table? This is one of the problems that you'll see when the stats are wrong. The second access plan is an index path where it uses an index to read a table. And it might scan 1 or more index paths, and it will tell you which indexes it's using if it's going to use an index path. Third one, which is kind of fun, is auto index path. And this is where the optimizer says, there should be an index here. There isn't one, so I'm going to create a temporary index. Now that's a temporary index. As soon as that query is over, that index is dropped. But the optimizer does do that in some cases, and I'll show you an example in a few minutes. When you see that, that might be a clue that you should go create an index on that field, especially if you see that being used a lot. The final access plan is remote path. And this basically means this table you're accessing is on a remote server and I don't know anything about it. It sends that part of the query to the remote server and depends on the remote server having the stats and sending the data back. This is very difficult, and the optimizer has no way of knowing how many rows are in that remote table. And so it may pick the wrong path here oftentimes. In fact, it doesn't pick the path. It sends the query, that part of the SQL, to the remote table. The remote server will then pick the path. Once you've got the data, you're always going to have, almost always have more than one table. There are two ways of joining tables. There's a dynamic hash join and a nested loop join. And they both work really well. When dynamic hash joins first came out, and I was one of them, had a lot of complaints about them. They work very well now, and I like to see them used. Dynamic hash join reads and builds a hash key on the join field. And then it reads the second table and dynamically builds a hash key and joins it real time. So it can be very efficient when you're joining two very large tables. In fact, it can be more efficient than using an index because it doesn't have to have the extra reads of reading an index. Now, nested loop join is very efficient when you're joining a big table to a small table, small tables. And you need to think about a nested loop join as a for each, where it reads one row in the primary table and then goes out and joins it with the secondary table. If there's an index there, that can be very efficient. If you're doing a nested loop join and you don't have an index, really bad, because then you're going to do a sequential scan on that second table multiple times. So let's take a look at what the Sqexplain.out looks like. And this is just an example from something I ran recently. It says select star from customer and state, joining on the state field, where zip equals some zip code and order by first name, last name. So the first thing the Sqexplain shows you is the query. Then it tells you the cost. And let me get my marker here so I can see if this will work. That's the cost that the optimizer has decided. So in this case, let's say there were 4 indexes on each table, plus a sequential scan. That would be 25 access ways for each table times 25. That'd be, I'm sorry, 5 access ways for each table times 5 would be 25 ways. Is the method it picked that had the lowest cost of all those 25 ways. Tells you this is how many rows it expects to return. And we'll come back to that because that will tell you whether your stats are right. And then it tells me that I have to have a temporary file to do a sort. And so after it's done the join and gotten the data back, it's going to do a sort, and it will require a temporary file for that. Anytime you see this, it means there's going to be a sort done at the end. Now, what it then tells me is that for the C table, which is the customer table, it's going to do a sequential scan. And it's going to read every row in that table. And then it's going to collect or filter the rows in this zip code. And then for the state table, it's going to use an index, and it's going to do a nested loop join. And based on that index, it's going to, and it tells me the name of the index here that it's using. It's going to go out and collect the states for that. So that's the first part of the query plan. And if you just do avoid execute, this is what you will see. The next part of the query plan okay, I'm stuck. The next part of the query plan is the stats. This is the results. And this doesn't get put into the SQL explain plan until the query is finished. And it says, okay, it created two internal tables, T1 and T2. T1 is for the customer table, T2 is for the state. Then it tells you each step it took. So it did one, let me put my marker back on. So it did one step, 3 step, 4 steps. First step is a scan, and it scanned T1, which is a customer table, and it tells you what the cost of that scan was and how many rows it scanned, how many rows it estimated would return, and how many rows it actually returned. This is a big clue. It thought there'd be 101,000, 10,100 rows. It only returned 4 rows. Stats were not right. That's the first clue this tells you. It also tells me the actual time it took. And then for the second table, the state table, it estimated there'd be 52 rows returned. There are only 4 rows returned. And it tells me the cost and the time for that. The nested loop join, which is the third step, joining the two tables. Again, it tells me that it estimated 10,100 rows, but only 4 were actually used. And it gives me the cost and the time for that. And the very last step is the sort. And again, it estimated a certain number of rows, and it tells me the sort. And it gives me the estimated cost. This is really helpful because you can look at this and say, okay, if I could get rid of that sort, bring the cost down. If I could make the sort more efficient, could I bring the cost down? If I had an index on that field where the sort was, could I bring the sort cost down? That's basically what this does, is it gives you the details of what each part of that query took to do. Now, let me get out of this. And let's go through some examples. And I'm going to go through some very simple examples at first. And we're going to get more complicated as we go through. The first example is a very simple select star from the stock table. This is in the DB Access demo database that we all love. Order by description. Now, because there's no where clause on this, it has to read every row in that table. And so a sequential scan is going to be the best read it. And because I have an order by, and there is no index on the description field, it has to do a sort and build a temporary file for that sort. So that gets me started on what is going on here. There's a second example, and this is where I have an index. So I'm saying select star from stock where unit price greater than 20, order by stock number. Now you notice there is no temporary file here. And that's because it's using the stock number to order the data. And let me get center of the screen. There we go. It's using the stock number to index to order the data. So it's reading the field instead of doing a sequential scan of the table. It's reading the stock index and returning the data already sorted by the stock index. Oh, there is an order by clause here, but no temporary file. That tells you it didn't have to sort the data. I saved a few steps there. The thing it tells you is this is the index it used. And the index is a composite index, but because stock number was the first field, it used the stock number in that index to read the data. So that's the second example. Now, something out, this little index path, this little bit right here, what does this all mean? Serial fragments all. What that tells you, and you'll either see serial or parallel. Serial means it's going to read one index fragment at a time. Parallel, that means it's reading all the index fragments at the same time. Usually you have to set PDQ priority to see parallel. If you don't have PDQ priority set, you'll almost always see serial. If you do have PDQ priority set and you don't see parallel, something else is going wrong, and that gives you a clue to go debug something. And then the fragments all means how many index partitions or fragments is it going to have to read. If it says all, it's going to have to read all the index fragments. Now, if the index only has one fragment, that's okay. But if it's a partitioned index, and really parallel and fragments being something other than all, only really makes sense on partitioned indexes. It will tell you the name of the fragment is reading. So let's say you have an index that is partitioned a year, and you do a query and you have year in the where clause. You should see, you may see serial, you may see parallel, but you'll see fragments, and you should see only that one partition with that 1 year. The name of that one partition will show up here. And that tells you, okay, you're not reading the whole index. You're reading just that one fragment of it. I know this can be kind of confusing. Most small tables, you will always see serial and fragments all. If you have a parallel PDQ, you'll see parallel here sometimes. And if your index is partitioned, you'll see the name of the fragments that it's reading. Yeah, this is one of my favorite types of queries, a key-only path example. Anytime you see this magic word, key only, right here, that means Informix got everything it needed from the index and did not even have to read the table. Let's say a table has 4 pages, a small table has 4 pages. The index probably only has 1 page. And so it got everything it needed. And the reason it got everything it needed, because I only asked for 1 field manufacturing code from that index. Instead of reading that table and doing a sequential scan and reading all 4 pages that that table was on, it read the 1 page the index was on and got everything you needed. This is a very efficient query. And there are a number of really, when you're building a database, things to think about. One example I like to use to get, and this is where key-only path is really helpful. Let's say you're looking up state sales tax all the time. And so you have a state table, and there's a field called state sales tax. Index with those 2 fields together will probably fit on 1 page. then you'll get key-only reads every time you have to look up a state sales tax. It doesn't have to read the state table. It gets it from the index. Another really good example is customer balance. You always are looking up your customer balance. Build an index that has a customer number and customer balance in it. That way it can go out there and get the customer balance very quickly just by reading the index without having to read the rest of the customer table. Now, if you need the rest of the customer table, then that won't work. But if all you need is a balance, this can be a very efficient way. And key-only indexes, very efficient read. Now, let's add some stuff to the where clause. We're going to say select star from stock, where a stock number is greater than 100 and less than 200. And the query comes along and says, okay, I'm going to use an index. This is the index I'm going to use. I'm going to read it in serial, and I'm going to read all fragments. There's only one fragment here. That's okay. And it tells me I'm going to start reading the index where it's greater than 100 and stop reading the index where it's less than 100. So this tells me it doesn't have to read the whole index. It's only reading a range of the index. This is also very efficient and very good use. Greater than 100, then it would have to read starting at 100, the rest of the index to find stock numbers greater than 100. Now let's expand it and let's put two tables in this example. And we're joining stock and items. And I'm going to say where stock number equal items number, and quantity is greater than 1. And it comes back and says, okay, do a sequential scan. Filter on quantity is greater than 1. And I'm going to then, for the stock table, use an index, do a nested loop join. And I'm going to join on the stock number. And it will go through and do a sequential scan on one table and then use the index to get the correct data from the next table. Dynamic hash join. Here I've got another scenario where I'm joining items in stock. This is a crazy query. You would never do this. Total price to unit price. That is absolutely crazy. It makes no sense. This would be a disaster, a Cartesian join. But to do this query, because I told it to, it will go out and it says, okay, I got to do a sequential scan on the stock table. I'm going to do a sequential scan on items table, and then I'm going to do a dynamic hash join those two tables. So while it's scanning the stock table, it's going to build a hash key in memory. And then when it scans the items table, it's going to build a hash key on the fly and use that to join with the data in memory with the stock. So that's what a dynamic hash join looks like. This is what a nested loop join looks like. And hopefully the nested loop join is on an index. If you see nested loop join and it says sequential scan here, that is really bad. That means that it's had to scan the whole table every time it had to join something. That's very inefficient. Yeah, this is the auto index example. I've got a query. This is from a long query, so I just cut out part of it. But it says, hey, I'm going to join the product table with an auto index, and boom, it creates that index on product code. This tells me I should create an index on product code. Then that would save this step, and it might be more efficient in the future. So those are some quick examples. I've got about 20 more examples I'm going to show you in just a couple of minutes. But before I jump into those examples, I want to talk about how we influence the optimizer. How do you get the optimizer to change its mind and use another path? The first and most important way is update stats. And this is my webcast next month. But this is probably the most important thing that you can do. If the statistics are up to date, the optimizer will choose the correct pass most of the time. The second thing you can do is Informix has query directives or query hints, optimizer hints. They're called in some other databases. And I'm going to give you an example of that. It's kind of interesting. I don't recommend doing it except in extreme cases. Usually the problem is you haven't done update stats. And I was working with a client doing an upgrade. Right after the upgrades, things did not run well. They put in a bunch of query directives, and the reason they hadn't run well was they hadn't done update stats after the upgrade, which is one of the first things you should do. Once they did update stats, they had all these query directives in, and as the data changed over time, the query, instead of being optimized for the new data, was stuck doing the old query method. And so query directives, when you use them, you've got to be very careful because you may actually pick a path that works really good now, but since you're overriding the optimizer in the future, it may not work very well. And you may be stuck with a slower query in the future when you do that. The other thing you can do is use parentheses. And it's really interesting how parentheses can affect a query. So all databases follow algebra. And in algebra, the logic is something in parentheses gets done first before anything else. And so you can use parentheses around things in your where clause and in your from clause to say, do these things first. Again, like directives, that can cause problems. A lot of times that actually is needed to get a query right. Indexes. If an index is missing, that will affect the optimizer. Adding an index. This is a great thing about a dynamic optimizer. You add an index, next time you run the query, the optimizer says, there's an index there, I can use it now. And it will use it and away you go. The selectivity of columns used in filters. The more selective, the more unique a column is, the better it's going to be to use it. And the last is there are many ways to write SQL. My colleague Art Cagle has a saying there are 100 ways to write one SQL statement. And that's really true. So the optimizer tries to dynamically optimize what you write. Does take what you write. And if you wrote something really bad, particularly with parentheses in the wrong place, it may not be able to optimize it very well. So two things the optimizer does do in the background, and I'm going to show you an example of this, is it does do query flattening and it does do query rewrite when it thinks it can improve performance. Query flattening is when it takes a subquery and turns it into a join. I once worked with a client that had these queries which had parentheses within parentheses within parentheses. And I was helping them improve their SQL. And what we found was by flattening the query manually, because the parentheses were there, the optimizer couldn't flatten it. But I flattened it manually. We got a query that was taking 4 or 5 hours down to minutes. And that's a huge performance improvement. The optimizer will also rewrite a query when it thinks it can get the same results. And I'm going to give you a couple of examples in just a few minutes. The performance of that query. Let's say, and the example I'm going to show you is you're joining customer state, and you put the clause on a field that's not indexed. And the optimizer can say, well, I can do that on this table where it is indexed and get the same results faster. So it might write the query for that. The goal is it won't rewrite the query if the results are going to be different. So hence to the optimizer. This is how you can, I call it temporarily fix poor stats. And you should always view hints as temporary fixes. I like to think if you ever use a directive, you should go submit a bug about that. You should not have to use directives. And I think it would be very helpful every time you use a directive to tell the optimizer team about why you need to do it. Make sure it's not because of poor stats. And the downside of directives is you may limit your performance in the future, because in the future, as the data grows and the data changes, if you have a directive in there, it can't. So there are a bunch of different types of directives: access method, join order, all these different directives. There's only really one I use and I find really helpful, and that is the index directive. Directives you enter with a comment and a plus sign. So it's dash dash plus, no space. Very important that the spacing is there. Or bracket plus, the kind of directive I use the most when I have to, and that's telling the optimizer to use this index, even if it thinks the index isn't right. And it will then use that index. There are access method directives. Avoid full means don't do any sequential scans. Full means do all sequential scans. You can also tell it to avoid an index or index all. And I'm going to give you some examples of these later on. So examples. I've got a whole bunch of examples I just want to go to. And really the purpose of this presentation is helping you understand the Sqexplain file and how it works. So I'm going to start DB Access, pick a database, go into my first example here. This is a simple sequential scan. And I'm going to put the explain file to a file. I give it a name, and it will create that file with that name in the current directory. I could put a path there. And if I'm working on a big project with a lot of people, I might do that, where that way all the explain files go to the same directory. And I'm going to create a report, and let me just hit run. And it says set explain, and then it sits there and it runs. It tells me it brought back 101,000 rows. So let's go look at this output file. So here's the output file. It tells me the cost 104,031. The bigger the cost, the more you should be concerned about it. I've seen costs go up into the millions. It tells me how many rows it expected to return, and it tells me it was going to do a sequential scan. And again, I would expect that because there is no where clause here. I told it, get me these fields. Doing a sequential scan is the best way. And then down here, it tells me, okay, internally, there's only one table, T1, and it scanned it in 0.14ths of a second. The estimated cost. My stats look good because it told me how many rows, the estimated rows and the actual rows is pretty much correct. Try a little bit more complicated one. I'm going to have an order by statement added to this. I run it, get the results. And the only difference really, you notice the cost has jumped quite a bit. And it says there's a temporary file required for the order by. And the key point here is sorts are one of the most expensive things. Look at the cost of the sort compared to just the cost of my sequential scan. My sequential scan hasn't changed. My sort has changed. And now my time has changed for that sort. So sorts are one of your most expensive SQL operations. I'm going to add a where clause. I'm going to add a where zip equals something on this customer table. It says, okay, I got 4 rows back. So let's go look at the Sqexplain file for that. Same thing, it needed a sort for the temporary file. It says now it's still doing a sequential scan. And I don't have an index on the zip code field. That's why it had to do a sequential scan. And this is where it gets interesting. It estimated that it was going to return 10,100 rows. It only returned 4. This is the first clue. Stats may not be right. And I see a couple questions in the chat. Hang on a minute. Get to them. Here are the stats. Look way off. And tells me update stats have not been done. Again, it only had 4 rows to sort. Even though it estimated more, the sort was quite a bit. That. Let's try the next one. Now I'm going to join two fields, 2 tables, the customer and the state table, just to see what happens when I do that. And it's again 4 rows retrieved. Come back here. Let's open up next one. This is why it's a good idea to name each one, each query with a separate explain out file. Then you can see it as it builds up. So it tells me that it's going to read the customer table first, state table next. It's going to use an index on the state table, and it's going to do a nested loop join. It has to do the sort. I have 4 steps now in the query. The scan of the customer table, that's T1, the scan of the state table, which is T2, using the index, nested loop join, and then the sort. And it gives me the breakdown and the cost of each step. And again, this allows you to see the optimizer is doing. I'm getting a little bit more interesting. Here I'm saying, let's join the customer and the state. I'm going to add a filter. Watch this very carefully because we'll see what happens with this filter. I'm going to add a filter on the state table for MD and a filter on the customer table for a zip code. It's done. Let's look at the results. It says, okay, look what it did. Instead of doing the filter on the state table, it put the filter in the customer table. This is query rewrite, where the optimizer said, I wanted me to filter on the state table, but that field is part of the join in the customer table, so I can do that filter earlier. That's what it did. It rewrote that query and put that filter earlier. This saves a step later on. It saves having a filter on that state table. And it only does that when it is sure that it'll get the same results. And it only does it really when there are filters where it could, particularly on join fields. That's an example of the optimizer rewriting a query. Write the query that way, and that would be more efficient too. Six. Now, this is an example where I have two filters on the state table. There's only one table here, but the optimizer has to decide which filter to use first, MD or the state name Maryland. Let's run it. Let's see what the optimizer picks. So it tells me it's using an index, and the index that the optimizer picked right here, which is on the state code name field. So what it does is it's using that index, and then it's doing a filter for, does the state name equal Maryland? And again, it picked this as the first field to use because that was indexed. And this is the kind of query that I like. It comes back so fast, took no time at all. Let's make this more interesting. Let's create an index. On the state name field, fields have an index. Let's see which one it chooses, because now it's going to have two indexes to choose from. So I'm dropping and recreating that index. And you see the create index shows up in my query plan. Picked the with the state code, the 2-character filter, because it decided that that index would be more efficient as the index path to use. So this tells me it's using an index path, and this tells me what index it's using in the path. So see if we can force it to use the other index. And I'm going to force it here to use that index with a directive. Let's run that. And see what query turns. What happens when you put a directive in? It says directives not followed. Well, I dropped the index. So it says, that index doesn't exist, so I couldn't follow that index. So let's go back and rerun the old one. I'm going to take out the drop index at the end. I'll run this. That index in there. Load this, and this is the first. It appended the second query. Now it says direct as followed, and now it follow that other index. Now what this is really helpful though is, let's say you want to add an index. You can sit here and look at the cost and say, well, did that index work faster than this index? You can look at the time and see. This is something very important when you're tuning queries, to look at the time and the estimated cost. But the time is really the more important thing. Did it run faster? The cost is lower, but the time is higher. It didn't run faster. The key thing in looking at this is this time field. See if that made a difference. So this is a little bit more complicated example. I'm going to see how many customers don't have any bills. And then I'm going to do a select, a join between the customers and the bills table. And there are about 600,000 bills in here, so this may take a minute run. 120 customers don't have bills. Let's see how many it does join. And the key in these next two queries, I want to show you the effect of an outer join on the cost and the time. And this in just a minute. With an outer join, we'll take a look at the cost and the time of that. Okay, let's go take a look at the cost for this. And count the index path to do that very quick. Now it did a regular join, and when the customers got the time. One thing I do a lot when I'm running this over and over again, I don't want to sit there and look at the SQL explains. Go grep cost. This tells me, okay, here's the cost of each part of the query. Then I can run it again, do a grep cost, and I'll see if my cost changed. Run the next one, which has an outer join. Only difference between these two is I'm looking at what an outer join cost. And sometimes you have to do outer joins, but mind the cost of what an outer join cost. You see it's taking a little bit longer time-wise. Okay, so let's come here and look at the cost for number 10. See the cost for the count and the subquery are the same. The outer join costs jump way up. And that was the point of that example. I'm almost out of time, but I'm going to run through some other quick examples here. One is comparing Informix joins with ANSI joins, with the self join, with the union and attempt, just because these are interesting queries. And then at the end, I'll take questions. I got somebody put in a really long question in the chat, and it did not get formatted well. Michael Hoffman, might be better to email me that question, Mike, because it didn't get formatted well in the chat. Okay, send me an email. So let's take a look at some more advanced examples. The outer join. So, and I have two of these. I'm going to do the second one because it's really very simple. Here I'm doing counts, and I'm going to do a count. Don't have a bill, and then I'm going to join the customers with a bill. This is an equal join. This is an outer join. And then this is an ANSI join. Because I get this all the time. Is there a difference between ANSI joins and Informix joins? And the answer should be no, but sometimes there is. And this is I did a advanced SQL class not too long ago, and this was one of the hot topics because we found in the class that taking some of their more complex queries and rewriting them as Informix outer joins instead of ANSI outer joins produced a faster result. Now they were on version 11, an older version, uh, and there's some other limiting factors there. But the key point I want to make is you should two queries or two ways of writing the same query. Run Sqexplain and look at the results before you decide which one to pick. So let's just run this and we'll take a look. This one is very simple. So this is the inner join, this is the outer join, inner join, outer join. The first one with Informix joins, the second one with ANSI joins. And 02. That's the grep. And you can see from the grep that the cost was the same, both for the joins and for the outer joins. In this example, I'm on version, if you do an onstat minus V, I'm on version 14. They should be the same, but sometimes they're not. And looking at the SQL EXPLAIN output can be very helpful. Let me, an or a union statement. This is another one. Found some versions an or statement will optimize better. On other versions, a union statement will optimize better. And so let me pick this as an example. I'm just going to run it. I have to run it all the way through to get both queries. For so the or clause, 7,759. I scroll down here. It's going to give me the cost twice, but it's quite a bit more. So in this example, the union, the same query results, but two ways of writing the query, one as a union, one as an or clause. The reason I point it out is in some versions and sometimes I've seen the union work better than an or. Again, it all depends on how many other things you have in the SQL explain in the query that you're doing. I have an example here with a derived query. This is always kind of fun. I'm going to build two temp tables and then join the two temp tables together, or I'm going to use a derived table, which is a select star from, and then this derived table is what my first temp table was. And I'm joining the second derived table there and joining them together. And I'm joining the same data twice. So the question is, perform better? And you should see that the derived table perform better than temp tables. And think of it this way, the temp table, these are three separate SQL statements. The derived table is one statement. If I come down here and let's just look at the cost. The first three costs are, you have to add them together. That's what the temp table query cost. Derived table costs not much more than just one of those queries. And this is what I do all the time when I'm optimizing SQL. I'll write it one way, write it another way, and then compare the cost and also compare the time. That can be very important. Like a case statement, I'm going to show you that. Here's an example of a query with no case statement, an example of a query with a case statement. Does a case statement expect change the cost? This is the data with no case statement, and then the case statement is telling me whether they're a good or a bad customer. This is key. Was that 7? So it looks like they both cost the same. But let's take a look at and I want you to look very carefully at this. The cost is the same, but look at the time. That's why you have to look at the time. The case statement cost me a fraction of a second more without a case statement. So in addition to the cost, the time is very important when you look at the data in your SQL EXPLAIN output. And this last one is a query rewrite. It's going to compare the performance of two queries. One is, and I did the rewrite here, they're both account. One is a subquery. One is rewriting that where it's not a subquery, but it's in the mainline query. Is that same results? Look at that. They're slightly different in this example. Again, you've got to look at them every time you do this. And then the last one I want to just do as an example is an update statement. Here I've got two update statements. And I want to see what the cost of them. This is on a indexed field. This is on a non-indexed field. Remember, you can do explain files on everything, not just SQL that is doing a select. It can be update, it can be delete, it can be insert, it can be a whole program. If you're writing in 4GL, you can turn this on at the beginning of a 4GL program and get everything in the 4GL program. There, I've done my update. Let's go look at the cost for this. The second one cost more than the first one. Let's look at the details for that. For the first one, it used an index path, and this is key. It did a key only on the state name equal New York. So it didn't have to read the state table. That's why that was so fast and efficient. The second one couldn't do that. It had to do a read on the table. Cost that much more, but it did end up costing a bit more. Those are just examples. I'm way out of time here, and I apologize for that. And I see if there are questions. If you have follow-up questions, please email me. I'll be glad to try and take a shot at answering them. You guys have been a great audience today. I would like to, before we end, just point out a couple of other things. Next month, November 21st, I'll talk about update stats, and I'm going to talk about AUS and manually doing them. Art has do stats a lot, and I'll talk about that a little bit too, but I say that mostly for Art. But I want to focus on how you do update stats manually and AUS. Next year, we are seriously considering launching a free Informix tutorials webcast series. Started with Informix. The most popular webcast we've done that's had over 5,000 views was on getting started with Informix. And working on something like that for next year, so stay tuned. Also want to point out we have 3 public courses planned for next year. We also do private courses. I have a lot of fun with private courses. I'm teaching one next. We do more private courses. And if you have 4 people that need to get trained, it's cheaper to do a private course. We can change it, we can tweak it for your environment. I had someone ask for a private course just on the SysMaster database. We're going to do an advanced course just on the SysMaster database next year for a customer. So we have fun with that. And if you do we have a classroom here. We can take 8 people. Student gets their own server. Servers are nice, powerful machines with 16 gigs of memory, SSD drive, and a bunch of disk for data. And right now, all the servers are running 1410. We also do a bunch of other things. Probably the biggest thing we do right now, besides training, is migrations and support. We do 24/7 remote DBA support, and then we do migrations. We've done several upgrades recently where we can take you from an old version to a new version. Or what I see a lot of people doing nowadays is migrating to a virtual machine from whatever version they're on. So with that, I will end. Again, if there are any quick questions, please put them in the chat. See any other questions there? So thank you all for attending, and I look forward to seeing you all next month when we talk about update stats. Have a good day. Bye now.